Okay, folks, now this video is going to talk about the normal distribution, but it's also going to talk about the so-called binomial distribution and how do we solve problems that are binary or are commonly referred to as binomial type problems. Okay, so this is the study guide for exam number 2. And this is chapters 6 through 9 study guide. And let's take a look here. Number 33 is the problem I want to look at. A biologist estimates that 70% of the deer in a region carry a certain type of tick. For a sample of 300 deer selected at random, what is the chance that 216 or fewer deer have this tick? Now, I'm sure you can see how this is a metaphor for other kinds of problems. In our current situation with a pandemic, the 70% could just as easily be people that are infected at a nursing home or whatever. Okay, so I just want to point that out. Okay, so here's my handwritten solution that I already sent out to you guys. Problem number 3, deer with ticks. And what I try to do sometimes on these, I wasn't 100% consistent, but I thought it might be helpful for you. I put down what the page number and the exercise or the example number was of a problem that was similar, so that if you're really struggling with this problem, you could go and look at this particular example on page 358. And then up here was kind of for my own benefit. I just wanted to kind of have an idea of what kind of a problem this is. It's a probability problem. We're going to use the normal distribution as an approximation for the binomial distribution. Okay, so here's what we're given. 70% of the deer in a population carry a certain tick. We take 300 deer at random. What we're supposed to find is the probability that 216, oops, hold on. 216 or fewer have this tick. So out of the 300, what's the probability that 216 of them or fewer have the tick? So it would be probability of 1, probability of 2, probability of 3, all the way up to 216. Okay? Well, as you can imagine, this is an absolutely impossible problem if we use the binomial distribution. Now let's think about this. Why is it a binomial type problem? It's a binomial type problem because 70% is the chance of a tick and 30% is the chance of no tick. So that's just like a heads or a tails, a success or a failure. So if you recall, that's what we mean by a binomial type distribution. Okay, so it would be impossible to do this problem. We'd have to do that crazy formula for the probability of 1 plus the probability of 2 plus the probability of 3. We just could not possibly do it. So what we have to do is we have to use the normal distribution to approximate it. So here's my cartoon. I get here's a normal distribution. Now, a true fact about the binomial distribution is that it's really, really simple to calculate the mean. Okay, the mu is n times p. Now, where does that come from? I sent this out to you. This is just the cover page. It's formulas, chapters 3 through 9. So what I did was I made a photocopy of the formula page, put a little handwritten note up on top here just to kind of refresh my memory what each of these is. Okay, so let's see if we can find that one. Okay, so the binomial distribution was discussed in chapter 5. And in fact, right here, here's the important terms. Binomial distribution was on page 277. Okay, so the formula for the binomial distribution is this monster here, which is very difficult to calculate. But the important thing I wanted to share with you is that the formula for the mean of the binomial distribution is just mu is equal to n times p. Do you remember that? And then we have the variance and the standard deviation is also very easy to compute. The variance is n times p times q. Now remember, n is just the number of events or the number of experiments or what have you. Okay, so it's very simple to make that calculation. It's very difficult to make this calculation. It's just very tedious. So we don't want to do that, do we? Okay, so let's go back. So mu is NP. So N is the number of deer that he's looking at. P is the probability of having the tick. So NP is 210. Sigma is NPQ. So multiply all of this out. And what do you get? You get 7.94. Okay, so we have mu of 210, sigma of 7.94, and that's what we need. Okay, so what we want is the probability of getting X. Now, X is the count. How many of these deer are infected? Okay, so is it 1? Is it 2? Is it 3? Is it 187? What is it? Okay, so the probability that X is less than or equal to 216. Okay, so that's what we're looking for. It's too hard to do it with a binomial distribution, so we're going to use the normal distribution. You need to remember that on the normal distribution, it like right here, 216. This is a normal distribution. It's a continuous distribution. So we have to have a continuous, we have to have a correction for continuity, they call it. Okay, so we don't go from 216, we go from 216 and a little bit, just a little tiny bit more to correct for the continuity. So the author calls it a continuity correction. So what we want is 216 plus 0.5. That's just a little tiny bit more than the 216. We're going to use the normal distribution to approximate the, oops, sorry, not as easy as it looks, folks. Give me 1 second here. Okay, a little technical difficulty there. Okay, we're going to use the normal distribution to approximate the binomial distribution. And as I said, we have to use a little continuity correction. Okay. Okay, and I've got this note here to myself. I'm not 100% sure what I meant by that. I apologize for that. But in any event, the Z, we know what the transformation is, okay? To go from Z, Z is equal to this. So if we want to go and find out what X is, we just do our thing here, okay? We crank this out. No, I'm sorry. If we want to find out what Z is. So we take X, take away mu, all of that over sigma. Okay. All right. Got a little thing popped up here. Let me get rid of that. Okay. That's going to give me my Z score. So my Z score is approximately 0.82. Okay. So going back up here, I was at 216 is what I wanted, 216 or less. I transform all of this information, all of these variables, I transform them into a Z-score, and it turns out that the equivalence or the corresponding Z-score is 0.82. So then if we look at table E, at 0.82, we can find out what the area is. So let's do that. Okay, 0.82. Here's table E. 0.8. Here's 0.80. Here's 0.81. Here's 0.82. 0.7939. 0.7939. There it is. Or another way of saying it is 79.39%. Or another way of saying it is, hey, it's about 0.794. So that, according to my note here, that's answer D. Let's take a look. Yeah, there it is. Answer D. Okay, so let's just get the big picture here. Big picture here is whenever you have a problem that you start out with data values that we normally call X, that's my random variable, the X. If I need to transform the X into a Z value, I just use the formula. It's just very, very trivial, very straightforward here, okay? Why do I do that? I do that because it is too hard to do the calculation using the original data values. I've got a formula for the normal distribution, but it's too hard. So what I do is I transform the original X's, I transform them into Z values. Once I have a Z value, I'm in great shape. I can do everything I need to do. I use the table to find, for example, the area under the curve to the left of this guy, to the left of 0.82. Okay, so anyway, I hope that helps.